Antarctica, beneath the ice. A hidden ocean world. When most people imagine Antarctica, they picture an endless expanse of white. A frozen continent locked beneath thick ice, silent and still, far removed from the movement and complexity of the rest of the planet. From above, it appears isolated, almost lifeless, a place defined by absence rather than activity. But this image, while powerful, is incomplete. Beneath the ice that covers Antarctica lies a hidden world that behaves in ways few once imagined. A world shaped not by air and wind, but by water. A world where the ocean moves quietly in darkness, carving, melting, and reshaping the ice from below. For decades, Antarctica was thought of primarily as land buried under ice. The focus of research centered on glaciers, snowfall, and surface temperatures. The ocean surrounding the continent was studied separately, treated as a boundary rather than a participant. What lay beneath the ice itself was assumed to be static, frozen solid, sealed away from the dynamic systems of the sea. But as technology advanced and measurements became more precise, this assumption began to weaken. Scientists started to realize that Antarctica is not only influenced by the ocean around it, but deeply connected to the ocean beneath it. Ice does not always rest on solid ground. Along much of Antarctica's coastline, enormous ice shelves extend outward over the sea, floating rather than anchored. These shelves appear motionless from above, yet beneath them, seawater flows continuously. This hidden circulation was once poorly understood, largely because it was so difficult to observe. And the environment beneath Antarctic ice shelves is among the most inaccessible on Earth. It is dark, pressurized, remote, and hidden beneath hundreds to thousands of meters of ice. Reaching it requires specialized tools, precise planning, and narrow windows of opportunity. For a long time, it remained out of reach. As scientists began to probe these hidden spaces, what they discovered challenged long-held beliefs. Beneath the ice, the ocean is not frozen in place. It moves. It carries heat. It interacts with the ice above in subtle but powerful ways. Instead of ice shaping the ocean alone, the ocean shapes the ice in return. This realization marked a turning point in how Antarctica was understood. The continent was no longer just a frozen mass responding passively to the atmosphere. It was part of an active ocean system, and one that operates largely out of sight. The phrase "beneath Antarctica" does not refer to a single environment. It encompasses a complex network of spaces where ice, water, and seafloor interact. There are cavities beneath ice shelves where seawater circulates slowly. There are channels carved into the underside of ice by moving water. There are subglacial basins where liquid water exists under immense pressure, insulated by ice from the freezing air above. Some of these waters are salty, connected to the ocean. Others are fresh, isolated for long periods. Together, they form a hidden marine system unlike any other on Earth. What makes this system particularly remarkable is its isolation. The water beneath Antarctic ice shelves does not experience sunlight, does not feel wind directly, and its movement is not driven by waves breaking on the surface. Instead, it is shaped by density differences, pressure, and the subtle exchange of heat between water and ice. These processes unfold slowly, often imperceptibly, yet their cumulative effect is profound. Over time, they can thin ice shelves from below, weaken their structure, and influence how ice flows toward the sea. For scientists, uncovering this hidden ocean world was not a single moment of discovery, but a gradual realization built from many pieces of evidence. Early measurements hinted at unexpected warmth beneath ice shelves. Later, sonar data revealed channels and cavities where none were expected. Chemical signatures in seawater suggested mixing between different water masses beneath the ice. Together, then these findings painted a picture of an environment far more dynamic than anyone had assumed. What made these discoveries especially striking was how quietly they emerged. There was no dramatic collapse, no sudden visual signal visible from space. The changes beneath Antarctica were subtle, detected only through careful measurement and patient analysis. This quiet nature is part of what made them so surprising. The ice above looked stable. The surface showed little sign of what was happening below. Yet beneath that calm exterior, the ocean was working continuously, reshaping the boundary between ice and water. The idea that warm ocean water could exist beneath Antarctica was particularly difficult to accept at first. In a region defined by extreme cold, the presence of water capable of melting ice from below seemed counterintuitive. But warm in this context does not mean warm by human standards. It means warm enough, relative to the freezing point under pressure, to slowly erode ice. Even a fraction of a degree matters. In the deep ocean beneath ice shelves, small temperature differences can have outsized effects over long periods. These discoveries forced scientists to rethink long-standing models. Ice sheets were no longer influenced solely by air temperature and snowfall. The ocean beneath them played a role that could not be ignored. This realization did not arrive all at once. It emerged gradually, as data accumulated and patterns became clearer. And as understanding grew, so did awareness of how much remained unknown. Studying the ocean beneath Antarctica is exceptionally difficult. Access is limited to short summer seasons. Key equipment must survive extreme cold, pressure, and darkness. Communication is restricted. Recovery of instruments is uncertain. Every mission carries significant risk, and failure can mean years of delay. These challenges are part of why much of what lies beneath the ice remained hidden for so long. They are also why discoveries made there carry such weight. Each new insight represents years of effort and careful planning. The shock associated with these discoveries does not come from sudden drama, but from implication. The realization that the ocean beneath Antarctica is active means that ice loss is not only a surface phenomenon. It means that changes far from the continent in the surrounding ocean can influence what happens beneath the ice. And it means that processes occurring quietly in darkness may shape the future of the ice sheet above. Yet even as understanding has grown, scientists move cautiously. The environment beneath Antarctic ice is fragile and largely undisturbed. Introducing equipment carries the risk of contamination. Disturbing sediments or water flows could alter conditions that have remained stable for thousands of years. Researchers are acutely aware of this responsibility. Exploration is balanced with restraint. Discovery is pursued carefully, with an awareness that some systems are better observed than disturbed. This cautious approach contributes to the sense that the ocean beneath Antarctica is avoided. In reality, it is respected. Scientists recognize both its importance and its vulnerability. They also recognize the limits of current technology. While some areas have been sampled, vast regions remain unmeasured. The map beneath the ice is still incomplete, marked by uncertainty and inference rather than direct observation. What lies beneath Antarctica is not a single shocking revelation, but a series of interconnected findings that collectively reshape understanding. A hidden ocean world, active yet unseen. A system where ice and water interact in ways that were once thought impossible. A reminder that even in the coldest, quietest places on Earth, movement and change persist. The Southern Ocean is not empty. From the edge of the Antarctic continent, The Southern Ocean stretches outward in all directions, vast, cold, and seemingly uniform. At the surface, it often appears empty, an expanse of dark water broken only by drifting ice and distant storms. For a long time, this emptiness shaped how the ocean around Antarctica was understood. It was viewed as a barrier, a hostile moat separating the frozen continent from the rest of the world. But beneath that surface, the Southern Ocean is anything but empty. It is one of the most active and influential marine systems on Earth, and its behavior beneath and around Antarctica has reshaped scientific understanding in unexpected ways. The Southern Ocean is unique because it connects all major ocean basins. Unlike other oceans, it is not enclosed by continents. Water flows around Antarctica in a continuous loop, driven by powerful currents that circle the globe. This movement allows heat, salt, and nutrients to be transported over enormous distances. What happens here does not stay here. Changes in the Southern Ocean can influence conditions far beyond Antarctica, linking the hidden world beneath the ice to the wider ocean system. For scientists, one of the most surprising realizations was how deeply the Southern Ocean interacts with the ice above it. The boundary between ocean and ice is not fixed. Water moves beneath ice shelves, exchanging heat and reshaping the underside of the ice. These interactions were once assumed to be minimal, but measurements began to tell a different story. Even in the coldest regions, seawater remains in motion, driven by density differences and pressure rather than wind. This movement allows relatively warmer water to reach the base of ice shelves, where it can slowly melt ice from below. The Southern Ocean's cold reputation can be misleading. While surface temperatures are low, the ocean is layered. Beneath the surface, water masses with different origins and properties move independently. Some originate far to the north, carrying heat accumulated over long journeys. As these waters circulate southward, they can slip beneath colder surface layers and reach the ice edge. There, even a small amount of heat can have a significant effect. Under high pressure, ice melts at slightly lower temperatures, meaning water that seems cold by human standards can still erode ice over time. This quiet delivery of heat was one of the most unexpected discoveries beneath Antarctica. Scientists had long focused on atmospheric warming as the primary driver of ice loss. The idea that the ocean could melt ice from below, out of sight, was initially difficult to accept. Yet repeated observations confirmed it. The instruments detected thinning ice shelves where surface temperatures alone could not explain the change. The source was below, not above. The Southern Ocean is also shaped by constant motion. Powerful currents sweep around the continent, interacting with underwater ridges and seafloor features. These interactions create complex patterns of flow, turbulence, and mixing. Where currents encounter ice shelves, they can be redirected beneath the ice, forming pathways that channel water deep into hidden cavities. These pathways were invisible for decades, known only through indirect evidence. When they were finally mapped, their scale surprised even experienced researchers. Another factor that sets the Southern Ocean apart is its role in global circulation. Cold, dense water formed near Antarctica sinks and spreads northward along the seafloor, driving a slow but persistent circulation that influences the entire planet. This process means that changes beneath Antarctic ice are not isolated. They are connected to global systems that regulate climate and ocean chemistry. Understanding what happens beneath Antarctica is therefore essential, not just for polar science, but for understanding the ocean as a whole. Despite its importance, studying the Southern Ocean is extraordinarily difficult. Harsh weather, frequent storms, and remote location limit access. Ice conditions change rapidly. Instruments must survive extreme cold and mechanical stress. Ships operate under constant constraint, with narrow windows for safe deployment. These challenges contribute to the impression that the region is avoided. In reality, it is studied carefully and selectively, with an awareness of its complexity and power. The idea of emptiness fades quickly when measurements are examined closely. Beneath the surface, the Southern Ocean is layered with moving water masses, each carrying its own temperature, salinity, and history. Chemical signals reveal mixing between deep and shallow layers. Traces of distant origins appear in water samples collected near Antarctica, evidence of long journeys through the global ocean. This hidden connectivity reinforces the idea that Antarctica is not isolated, even beneath its ice. What shocked scientists was not just the presence of movement beneath the ice, but its persistence. The ocean does not pause beneath Antarctica. It does not freeze into stillness. It continues to circulate, season after season, year after year. And this persistence means that even slow processes can accumulate into significant change. A millimeter of melting each year becomes meters over centuries. Subtle thinning weakens ice shelves, altering how they support the ice behind them. The Southern Ocean also plays a role in shaping the seafloor beneath Antarctica. Currents transport sediment, carve channels, and reshape the terrain below ice shelves. These changes influence how water flows in the future, creating feedback loops that are difficult to predict. For scientists, this dynamic environment resists simple models. It demands continuous observation, yet continuous observation is rarely possible here. The realization that the Southern Ocean is an active participant beneath Antarctica marked a shift in scientific thinking, when the ice sheet was no longer viewed as a static block, responding only to the air above it. It became part of a living system, interacting with the ocean in complex ways. This shift did not happen overnight. It emerged slowly as data accumulated and assumptions were questioned. Even now, much of the Southern Ocean's behavior beneath Antarctic ice remains uncertain. Large areas have never been directly measured. Models rely on limited observations and careful inference. Scientists know enough to recognize the importance of what lies beneath the ice, but not enough to describe it fully. This gap between knowledge and understanding is part of what makes discoveries here feel so profound. Ice shelves and the ocean below. At the edge of Antarctica, the ice does not end abruptly. Instead, it stretches outward, extending over the sea in vast floating platforms known as ice shelves. From above, these shelves appear solid and permanent. Thick slabs of ice anchored to the continent and drifting quietly over the ocean. For a long time, they were thought of as passive features, frozen extensions of land, shaped primarily by snowfall and surface temperature. What lay beneath them was assumed to be cold, still, and largely irrelevant. That assumption turned out to be one of the most significant misunderstandings in polar science. Ice shelves are not grounded like the glaciers behind them. They float. This simple fact changes everything. Beneath each shelf lies a hidden cavity where ocean water circulates continuously. These cavities can be enormous, stretching hundreds of kilometers inland and reaching depths of several hundred meters. They are completely dark, under immense pressure, and sealed from direct observation by thick ice above. For decades, scientists had little direct information about what happened inside them. Yet these spaces turned out to be some of the most important interfaces between ocean and ice on the planet. The ocean beneath ice shelves behaves differently from open water. There is no wind-driven mixing, no waves, no direct contact with the atmosphere. Movement is driven instead by subtle differences in temperature and salinity, and by the shape of the cavity itself. Water enters beneath the shelf, flows along the underside of the ice, and exits again, carrying with it heat, salt, and meltwater. This circulation is slow, often measured in centimeters per second, but it is relentless. Over time, it reshapes the ice from below. One of the most surprising discoveries was how sensitive ice shelves are to the water beneath them. Scientists found that small changes in ocean temperature could lead to significant changes in melting rates. The underside of an ice shelf is not smooth. It is shaped by channels, ridges, and cavities carved by flowing water. As water moves along these features, it concentrates melting in specific areas, thinning the ice unevenly. This thinning weakens the shelf's structure, reducing its ability to support the glaciers behind it. The role of ice shelves is not just to float. They act as braces, slowing the flow of ice from the continent into the ocean. When an ice shelf thins or weakens, that braking effect is reduced. Glaciers upstream can accelerate, delivering more ice to the sea. This connection between the ocean beneath ice shelves and the ice sheet above was not fully appreciated until detailed measurements began to emerge. What shocked scientists was not just that melting occurred from below, but how strongly it influenced the entire ice system. Accessing the ocean beneath ice shelves is extraordinarily difficult. Drilling through hundreds of meters of ice requires specialized equipment and careful planning to avoid contamination. Autonomous underwater vehicles must navigate in total darkness, with no GPS, relying on pre-programmed routes and limited communication. Even small errors can result in vehicles becoming lost beneath the ice. As a result, only a handful of ice shelf cavities have ever been explored directly. Each exploration has revealed unexpected complexity. In some cavities, the scientists discovered channels carved deep into the ice by persistent water flow. These channels act like hidden rivers, guiding warm water far beneath the ice. Their existence explained patterns of thinning that had puzzled researchers for years. Surface measurements showed ice thinning in areas where atmospheric warming alone could not account for the change. The answer lay beneath, in the shape and movement of water hidden from view. The ocean beneath ice shelves also carries meltwater away from the ice. As ice melts from below, fresh water mixes with seawater, altering its density and movement. This mixture influences circulation both within the cavity and beyond it, affecting how water flows along the continental shelf and into the wider Southern Ocean. These feedbacks are complex and still not fully understood. What is clear is that ice shelves are not isolated features. They are active participants in a larger ocean system. For scientists, this realization required a shift in perspective. Ice shelves could no longer be treated as static boundaries. They became dynamic interfaces where ocean processes exert direct control over ice behavior. This shift had profound implications for how Antarctic stability was assessed. Models that ignored or simplified under-ice ocean circulation began to fall short. New approaches were needed, ones that acknowledged the hidden complexity beneath the ice. The discovery of active circulation beneath ice shelves also raised new questions. How far inland does warm water penetrate? How quickly do cavities respond to changes in the surrounding ocean? Are some shelves more vulnerable than others due to their shape or location? Answering these questions requires long-term observation. Yet, long-term observation beneath ice shelves remains exceptionally challenging. Despite these challenges, each new measurement reinforced the same message. The ocean beneath Antarctica is not passive. It is not frozen in place. It moves, it carries heat, and it shapes the ice above it in ways that are both subtle and powerful. The shock for scientists was not the presence of water beneath the ice, but the realization that this water was quietly controlling processes once attributed almost entirely to the atmosphere. Ice shelves now occupy a central place in Antarctic research. They represent the meeting point between sea and ice, where changes in the ocean are translated into changes in the ice sheet. Though understanding them requires understanding what flows beneath them, how that flow evolves, and how it responds to forces far beyond Antarctica itself. Warm ocean water beneath Antarctic ice. For much of scientific history, Antarctica was defined by one simple idea: cold, extreme cold. A place where ice formed faster than it could ever melt, especially far beneath the surface. The idea that ocean water warm enough to melt ice could exist beneath Antarctica seemed contradictory, almost impossible. Yet this was one of the most unsettling discoveries scientists made as they began to study what lay beneath the ice shelves. Not dramatic warmth, not heat in the human sense, but water just warm enough to change everything. In the deep ocean, temperature behaves differently than it does at the surface. Water does not need to be warm to melt ice. And under high pressure, the freezing point of seawater is lower. This means that water that would feel painfully cold to human skin can still erode ice slowly and persistently. Beneath Antarctic ice shelves, scientists detected water that hovered just above this pressure-adjusted freezing point. The difference was often less than a single degree. Yet over time, that small difference proved powerful. What shocked researchers was not only the presence of this warmer water, but its source. Much of it originated far from Antarctica. Water masses formed in distant regions of the ocean slowly traveled southward, carrying heat accumulated over long journeys. As they approached the Antarctic continental shelf, they did not remain at the surface. Instead, differences in density allowed them to slip beneath colder surface layers and move inward, thus guided by seafloor contours and hidden pathways beneath the ice. Once beneath the ice shelves, this water became trapped in cavities where it could circulate for extended periods. With no exposure to the atmosphere, it retained its heat. As it flowed along the underside of the ice, it transferred that heat directly to the ice base. This process did not produce visible cracks or dramatic collapse. It produced thinning, slow, uneven thinning that was almost invisible from above. For years, satellite observations showed ice shelves thinning in specific regions, but the cause was unclear. Surface air temperatures alone could not explain the patterns. Snowfall remained relatively stable. The answer, it turned out, was below. Our sonar measurements and temperature sensors revealed warm water flowing through channels carved into the underside of the ice. These channels focused melting in narrow zones, weakening the ice from within. This discovery forced a fundamental reassessment of Antarctic stability. Ice shelves had long been treated as buffers, protecting the ice sheet from rapid change. But if the ocean beneath them could thin them silently, that protection was far more fragile than assumed. The shock was not that melting occurred, but that it occurred without obvious warning signs at the surface. Scientists also discovered that the shape of the ice itself influenced how warm water moved beneath it. Deep grooves and ridges on the ice base acted like guides, steering water toward specific regions. Once melting began, it often reinforced itself. Alberta meltwater altered local circulation, allowing more warm water to reach the ice. This feedback loop made certain ice shelves far more vulnerable than others, depending on their geometry and location. What made this discovery particularly unsettling, remember, is its invisibility. There was no plume of steam, no surface flooding, no sudden collapse. The ice above looked calm, unchanged, even as it thinned from below. Only precise instruments, placed at great risk beneath the ice, revealed the process unfolding. Studying this warm water is extraordinarily difficult. Instruments must survive crushing pressure, near freezing temperatures, and complete darkness. Autonomous vehicles must navigate without GPS, relying on pre-programmed routes beneath unstable ice. Communication is limited. Recovery is uncertain. Each successful measurement represents years of planning and narrow windows of opportunity. Many attempts fail, leaving data incomplete and questions unanswered. Yet even with limited data, the pattern became undeniable. Warm ocean water was present beneath Antarctica, and it mattered. It meant that changes in distant parts of the ocean could influence ice thousands of kilometers away. It meant that Antarctica was not insulated from the rest of the planet by cold alone. It was connected through the sea. This realization transformed how scientists understood risk beneath Antarctica. The ocean was no longer just a boundary around the continent. It was an active force beneath it, a slow, quiet agent of change that could operate for centuries without drawing attention. The shock, then, was not dramatic discovery, but deep implication. Beneath Antarctica, warmth exists where none was expected. And that warmth, subtle and persistent, has the power to reshape ice that once seemed eternal. Subglacial seas beneath Antarctica. Long before scientists ever confirmed their existence, the idea of liquid water beneath Antarctica seemed implausible. A continent buried beneath kilometers of ice was assumed to be frozen solid from top to bottom, sealed away from movement and change. Yet careful measurements began to suggest otherwise. Subtle variations in ice surface elevation, unexpected reflections in radar data, and unusual patterns in ice flow hinted at something hidden below. What these clues revealed was one of the most surprising discoveries beneath Antarctica. Vast bodies of liquid water trapped under the ice, known as subglacial seas. These subglacial seas exist not at the edges of the continent, but deep beneath it, sealed beneath immense pressure and complete darkness. The ice above them acts as an insulator, trapping heat generated by the Earth itself. Combined with the crushing weight of the ice, this heat is enough to keep water in a liquid state, even in an environment where surface temperatures are far below freezing. For scientists, confirming the presence of these hidden seas fundamentally changed how Antarctica was understood. What makes these subglacial seas especially remarkable is their isolation. Many have been sealed beneath the ice for hundreds of thousands and possibly millions of years. They do not experience seasonal cycles. They are not mixed by wind or waves. Their water moves slowly, if at all, driven by pressure gradients and subtle interactions with the ice above and the seafloor below. This isolation creates environments unlike any other marine system on Earth. Some subglacial seas are fresh, formed from melted ice. Others show signs of interaction with seawater, suggesting hidden connections to the ocean beneath ice shelves. This discovery blurred the line between terrestrial ice systems and marine environments. Beneath Antarctica, freshwater and seawater may interact in ways that are still poorly understood, creating complex chemical and physical conditions beneath the ice. Mapping these hidden seas is extremely challenging. Scientists cannot simply drill freely through the ice. Any attempt to access these environments risks contamination, introducing microbes or chemicals that could permanently alter pristine systems. Instead, much of what is known comes from indirect observation. Radar waves penetrate ice and reflect off liquid water. Gravity measurements reveal density differences beneath the surface. Satellite data tracks subtle movements of the ice sheet above, movements influenced by water flowing below. As evidence accumulated, scientists began to realize that subglacial seas are not isolated pockets, but part of a larger network. Channels beneath the ice connect lakes and seas, allowing water to move slowly across the continent. This movement can influence how ice flows above, lubricating the base of glaciers and altering their speed. Beneath Antarctica, water is not merely present, it is active. The discovery of this hidden water network shocked scientists because it revealed a dynamic system operating where stillness was assumed. The ice sheet was no longer resting on a frozen foundation. In places, it was floating, sliding, or deforming over liquid water. This realization forced a reassessment of how stable the Antarctic ice sheet truly is over long timescales. Studying subglacial seas directly remains one of the greatest challenges in Earth science. Drilling requires sterile techniques, extreme precision, and years of planning. Equipment must function under immense pressure and total darkness. Communication is nearly non-existent. Even when access is achieved, sampling must be minimal to avoid disruption. For these reasons, only a handful of subglacial environments have ever been touched directly. What scientists have learned so far suggests that these seas are chemically unique. Long isolation allows minerals to dissolve into the water. Gases become trapped. Chemical reactions proceed slowly, shaped by pressure rather than temperature. These conditions raise profound questions about the nature of life and the limits of habitability beneath Antarctica. The existence of subglacial seas also links Antarctica's interior to its margins. Water flowing beneath the ice can eventually reach the ocean, carrying chemical signatures that reveal its long journey. This connection means that what happens beneath the continent does not remain confined there. It becomes part of the broader ocean system, influencing circulation and chemistry beyond the ice. The shock of discovering liquid seas beneath Antarctica lies not only in their presence, but in what they represent. A hidden hydrological system operating beneath the largest ice mass on Earth. A reminder that even in the coldest, most isolated places, ours, liquid water persists. And where liquid water exists, change follows. Pressure and darkness beneath kilometers of ice. Beneath Antarctica, pressure and darkness define everything. They are not occasional conditions, but permanent realities that shape the hidden ocean world below the ice. As ice thickens above, pressure increases relentlessly. Every additional meter adds weight, compressing water, sediment, and anything placed within this environment. For scientists, this pressure is not just a physical force, but a boundary that limits access, observation, and understanding. Under kilometers of ice, pressure reaches levels far beyond anything experienced at the surface of the ocean. Water behaves differently here. Its freezing point shifts. Chemical reactions slow or change direction. Materials deform in ways that are difficult to predict. Instruments must be engineered with extreme precision to survive, and even then, failure is common. A seal that works perfectly in laboratory conditions may fail silently after months beneath the ice, ending a mission without warning. Darkness compounds these challenges. No sunlight penetrates through the ice. There are no day-night cycles, no seasonal light changes, no visual reference points. This darkness is absolute. Any observation must rely on artificial light, which itself alters the environment. Light introduces heat. It disturbs sediments. It changes the behavior of any organisms present. For scientists, this creates a paradox. To observe is to interfere. Navigation beneath Antarctic ice is especially difficult. Without GPS signals, autonomous vehicles must rely on internal guidance systems and acoustic communication. Errors accumulate slowly. A slight deviation can send a vehicle drifting into unseen terrain or beneath unstable ice. Recovery becomes uncertain, and once contact is lost, it is rarely regained. Many missions end not with dramatic failure, but with silence. Pressure and darkness also affect time. Processes unfold slowly beneath Antarctica. Water moves at measured paces. Chemical changes take years or centuries. Ice melts from below at rates almost imperceptible in the short term. To understand these processes, scientists need long-term data. Yet maintaining long-term instruments under such conditions is extraordinarily difficult. Batteries degrade faster, sensors drift. Maintenance is impossible. Each deployment is a gamble against time itself. These conditions explain why so much beneath Antarctica remains unmapped. Scientists cannot simply observe continuously. They must rely on brief glimpses, fragments of data collected over short windows. From these fragments, they attempt to reconstruct systems that operate over vast timescales. The uncertainty this creates is unavoidable, and it shapes how discoveries are interpreted. Pressure also isolates subglacial environments from the outside world. Water trapped beneath ice is not easily exchanged. Once isolated, it remains so for immense periods. This isolation preserves chemical signatures and ancient conditions, but it also means that disturbances linger. Any change introduced by scientific activity may persist far longer than intended. This risk reinforces cautious approaches and limited intrusion. The darkness beneath Antarctica is not empty. It hides motion, chemistry, and interaction. Yet because it cannot be seen directly, understanding relies on indirect evidence. Temperature anomalies, salinity shifts, pressure changes. Each measurement offers a clue, but never the full picture. Scientists must assemble these clues patiently, aware that much remains concealed. The shock of these discoveries is not rooted in spectacle. It lies in contrast. Beneath one of the brightest, most reflective surfaces on Earth lies a realm of complete darkness. Beneath ice that appears solid and unchanging lies water under immense pressure, moving, melting, and reshaping the foundation of the continent. This contrast forces scientists to reconsider assumptions about stability and permanence. Pressure and darkness are not obstacles to be overcome once. They are constant companions beneath Antarctica, defining what is possible and what is not. And they explain why progress is slow, why data is incomplete, and why so many questions remain unanswered. Beneath the ice, the environment dictates the pace of discovery. Ocean currents trapped beneath the ice. Beneath the vast ice covering Antarctica, the ocean does not rest. Even in total darkness and under immense pressure, water continues to move. These movements are not driven by wind or waves, but by subtle differences in temperature, salinity, and pressure. For a long time, scientists assumed that water trapped beneath ice shelves and within subglacial cavities would be largely stagnant. What they discovered instead was a slow but persistent system of currents, flowing quietly beneath the ice and reshaping Antarctica from below. These trapped currents are difficult to detect. They move far more slowly than surface currents, and often at speeds measured in centimeters per second. Yet their influence accumulates over time. As water flows beneath the ice, it transports heat and salt, subtly altering the environment it passes through. Even slight warming can increase melting at the ice base, while changes in salinity affect water density and circulation patterns. These interactions form feedback loops that scientists are still struggling to fully understand. One of the most surprising findings was how far these currents could travel beneath the ice. In some regions, water entering beneath an ice shelf does not exit nearby. Instead, it follows winding paths guided by the shape of the seafloor and the underside of the ice, reaching far inland before turning back toward the open ocean. This means that changes in ocean conditions at the edge of Antarctica can influence ice hundreds of kilometers away, hidden from direct observation. The pathways these currents follow are shaped by features carved into the ice itself. Grooves, channels, and ridges on the underside of ice shelves act like invisible riverbanks, steering water along preferred routes. Over time, flowing water deepens these channels, reinforcing the pathways and allowing more heat to reach the ice. This process explains why melting beneath ice shelves is often uneven, concentrated in specific zones rather than spread evenly across the ice base. Currents beneath Antarctica also interact with subglacial water systems. Fresh water produced by melting ice mixes with saltier seawater, creating layers that influence circulation. In some areas, lighter freshwater rises and spreads, while denser seawater sinks and flows inward. These layered flows add complexity to an already difficult environment, making it challenging for scientists to predict how changes will propagate through the system. Measuring these hidden currents is one of the greatest challenges in polar oceanography. Instruments must be placed beneath ice shelves or lowered through narrow access holes drilled into the ice. Once deployed, they must operate autonomously for months or years, collecting data without maintenance. Communication is limited and recovery is uncertain. Many instruments never return, taking their data with them. Each successful dataset represents a rare glimpse into a system that remains largely concealed. Despite these limitations, the data collected so far has revealed a crucial truth. The ocean beneath Antarctica is not isolated from the rest of the world. It is connected through slow-moving currents that respond to changes in the broader Southern Ocean. When conditions shift at the continental shelf, those changes can ripple inward beneath the ice, influencing melting patterns and ice stability far from the coast. This discovery altered how scientists think about cause and effect beneath Antarctica. Ice loss was no longer seen as a purely local response to local conditions. Instead, it became part of a larger, interconnected system. Heat delivered quietly by trapped currents could weaken ice shelves over long periods, setting the stage for more visible changes later. The shock of these findings lies in their subtlety. There are no roaring flows, no dramatic surges. The currents beneath Antarctica operate patiently, almost invisibly. Yet they persist year after year, shaping ice and water alike. Their slow pace makes them difficult to study, but also makes their impact profound. Understanding these hidden currents is essential for predicting Antarctica's future. Yet much remains unknown. Many pathways have never been mapped. Many regions remain unsampled. Scientists work with fragments of information, piecing together a picture that is still incomplete. Each new measurement refines that picture, but also reveals how much remains to be learned. The Antarctic seafloor, hidden beneath ice. Beneath the moving water and the towering ice above it lies another layer of the Antarctic system that long remained unseen. The seafloor. For many years, scientists imagined the ground beneath Antarctica's ice shelves as relatively simple, flat, cold, and unchanging. But as more detailed measurements became possible, this assumption quietly unraveled. The seafloor beneath Antarctic ice is not a stable platform. It is uneven, fractured, and shaped by forces that continue to act upon it, even in complete darkness. Much of the Antarctic seafloor is covered in thick layers of sediment rather than solid rock. These sediments have accumulated over immense spans of time, settling slowly in an environment where movement is subtle but persistent. Under pressure from ice and water, this sediment can behave unpredictably. It may compact, shift, or deform in response to changes above. For scientists attempting to place instruments or interpret measurements, this instability adds another layer of uncertainty. Mapping the seafloor beneath ice shelves is exceptionally difficult. Traditional mapping methods rely on ships and sonar, but ships cannot pass beneath ice. Instead, scientists must depend on autonomous vehicles or indirect signals that pass through ice and water. These methods provide limited resolution, revealing only broad shapes rather than fine detail. As a result, many features beneath Antarctic ice are inferred rather than directly observed. Valleys, ridges, and channels may exist undetected, shaping how water moves and where heat is delivered. When portions of the seafloor were finally mapped in detail, the results were surprising. Deep troughs extended far inland beneath the ice, creating pathways for ocean water to reach regions once thought isolated. These troughs guide currents beneath ice shelves, allowing warmer water to penetrate deeper than expected. Or their existence helps explain why melting is often concentrated in specific areas, far from the visible edge of the ice. The seafloor also bears the marks of past change. Ancient channels carved by flowing water suggest that ice and ocean interactions have been reshaping Antarctica for far longer than modern observation can capture. These features hint at cycles of advance and retreat, of melting and refreezing that occurred under conditions very different from today. Understanding this history is crucial, but evidence is fragmentary, buried beneath ice and sediment. For scientists, the instability of the seafloor presents practical challenges. Instruments placed on soft sediment may sink, tilt, or become buried over time. Cables may shift or break. Measurements taken at one moment may not reflect conditions months later, not because the environment has changed dramatically, but because the ground beneath the instruments has moved. In such an environment, long-term observation becomes especially difficult. The seafloor also interacts with the ocean chemically. Sediments can release or absorb substances, altering the chemistry of the water above. In regions beneath ice shelves, where water circulation is slow, these chemical exchanges can accumulate, creating localized conditions that differ sharply from surrounding areas. Detecting and interpreting these signals requires careful measurement and cautious analysis. Another complicating factor is tectonic influence. Antarctica rests on a complex geological foundation shaped by ancient forces. While most tectonic activity beneath the continent is subtle, even small movements can affect sediment stability and seafloor shape. Over long periods, these changes influence how water flows beneath the ice, reinforcing or redirecting currents in ways that are difficult to predict. The shock for scientists was not the presence of complexity beneath Antarctic ice, but the extent of it. The seafloor was not a passive boundary beneath the ocean. It was an active participant, guiding water movement and influencing melting patterns above. This realization forced researchers to reconsider models that treated the ice-ocean boundary as a simple interface. Studying the seafloor beneath Antarctica remains one of the most demanding tasks in Earth science. Access is rare, data is limited, and uncertainty is unavoidable. Yet each new piece of information reveals a system far more dynamic than once imagined. Beneath the ice, the ground itself plays a role in shaping Antarctica's future. Massive channels carved beneath the ice. As scientists began to piece together data from beneath Antarctica's ice shelves, a pattern emerged that was both unexpected and unsettling. Hidden beneath kilometers of ice, the ocean had carved enormous channels, structures so large and deeply etched that they could not be explained by chance or short-term processes. These channels, invisible from the surface, revealed that the ocean beneath Antarctica had been actively reshaping the ice for far longer and more intensely than anyone had realized. The first hints came from sonar readings and radar reflections that did not align with existing models. Instead of a relatively smooth ice base, like instruments detected deep grooves and tunnel-like features extending inland beneath ice shelves. At first, these signals were treated cautiously. The environment beneath Antarctica is notoriously difficult to measure, and false readings are common. But as more data accumulated, the evidence became impossible to ignore. The channels were real, and they were vast. Some of these channels stretch for tens of kilometers, cutting upward into the underside of the ice like slow-moving rivers turned upside down. They are carved not by air or surface meltwater, but by ocean currents flowing persistently beneath the ice. Over time, slightly warmer water follows the same pathways again and again, deepening the channels and reinforcing their structure. This focused melting concentrates ice loss in narrow zones, weakening ice shelves from below. What shocked scientists most was the scale. These were not small features formed over decades. They were massive formations that suggested long-term interaction between ocean and ice, operating quietly over centuries or longer. The existence of such channels implied that the ocean beneath Antarctica was far more organized and directional than previously thought. Water was not merely circulating randomly. It was being guided by the shape of the ice and the seafloor into defined routes. These channels also explained mysteries observed at the surface. Satellite data had shown areas of ice thinning that did not match atmospheric patterns. Snowfall remained steady, and surface temperatures alone could not account for the changes. The answer lay below. Where channels existed, melting was intensified from beneath, thinning the ice above without leaving obvious surface clues. The formation of these channels creates a powerful feedback loop. As a channel deepens, it allows more warm water to flow through, increasing melting and further enlarging the pathway. Over time, this process can significantly weaken an ice shelf, reducing its ability to support the ice sheet behind it. What makes this especially concerning is how quietly it occurs. There is no sudden collapse, no dramatic surface fracture, just gradual thinning that accumulates over long periods. Mapping these channels is extremely difficult. Autonomous vehicles must navigate beneath unstable ice in total darkness, often without knowing the full shape of the terrain ahead. Many missions end early due to navigation challenges or equipment failure. As a result, the scientists believe that many channels remain undiscovered, hidden beneath regions that have never been directly explored. The discovery of these channels forced scientists to reconsider long-held assumptions about Antarctic stability. Ice shelves were no longer uniform barriers. They were sculpted from below by ocean processes that could concentrate stress in specific regions. This realization shifted research priorities, placing greater emphasis on understanding under-ice circulation and its long-term effects. These channels also link the seafloor to the ice above. Their paths are often guided by depressions and troughs in the underlying terrain, revealing a deep connection between geology and ice dynamics. Changes in one layer influence the others, creating a system where ice, ocean, and seafloor are tightly intertwined. The shock of discovering these hidden channels lies in their implication. Beneath Antarctica, the ocean has been quietly at work, carving structures large enough to influence the fate of entire ice shelves. These discoveries did not arrive with spectacle or drama. They emerged slowly, through careful measurement and patient analysis. And yet, their significance is profound. Chemical signals from beneath Antarctica. Not all discoveries beneath Antarctica are visible as shapes, channels, or movement. Some of the most revealing evidence comes from what cannot be seen at all. Dissolved within the water beneath the ice are chemical signals, subtle fingerprints that record where the water has been, how long it has been isolated, and what it has interacted with along the way. For scientists, Then these chemical clues became one of the most powerful tools for understanding the hidden ocean beneath Antarctica, and they revealed a story far more complex than expected. When researchers first began sampling water near Antarctic ice shelves, they noticed something unusual. The chemistry did not always match what models predicted. Salinity levels, gas concentrations, and trace elements suggested that some water masses had been isolated for long periods, while others showed signs of recent mixing. These differences could not be explained by surface conditions alone. They pointed instead to processes occurring far beneath the ice, out of sight and beyond direct observation. One of the most important chemical indicators beneath Antarctica is salinity. Seawater becomes saltier or fresher depending on how it interacts with ice. When ice melts from below, it releases fresh water, lowering salinity locally. When ice forms, it expels salt, increasing salinity in surrounding water. By measuring salinity patterns beneath ice shelves, scientists were able to trace where melting was occurring and how meltwater moved through hidden cavities. These measurements revealed circulation patterns that had never been directly observed. Another crucial signal comes from dissolved gases, particularly oxygen. In open oceans, oxygen levels are influenced by contact with the atmosphere and biological activity. Beneath Antarctic ice, there is no direct contact with air. Any oxygen present must have entered long ago or been transported through slow circulation. When scientists measured oxygen concentrations beneath ice shelves and within subglacial waters, they found values that suggested long isolation in some regions and recent ocean contact in others. These findings help distinguish between ancient, trapped water and water actively exchanging with the Southern Ocean. Carbon chemistry provided further insight. Dissolved carbon compounds revealed how long water had remained isolated and whether it had interacted with sediments or biological systems beneath the ice. Some samples showed chemical signatures consistent with water that had been cut off from the atmosphere for extremely long periods. Others showed signs of mixing with seawater that had traveled great distances before reaching Antarctica. This chemical diversity confirmed that beneath the ice existed not a single environment, but a mosaic of connected and semi-isolated systems. Trace elements offered additional clues, as certain elements dissolve into water when it comes into contact with sediment or rock. Their presence beneath Antarctic ice suggested interaction between water and the sea floor, even in regions where direct contact was thought to be minimal. This meant that the hidden ocean beneath Antarctica was not simply flowing along the ice base, but also exchanging material with the ground below, further complicating its chemistry and behavior. Interpreting these chemical signals is extraordinarily challenging. Sampling opportunities are rare. Instruments must function under extreme pressure and cold. Contamination must be avoided at all costs. Even small errors can compromise results. Scientists often rely on a handful of samples to draw conclusions about systems that span hundreds of kilometers. Each data point carries enormous weight, and conclusions are reached cautiously. What made these chemical discoveries especially shocking was how clearly they contradicted earlier assumptions. Antarctica was once thought of as a frozen barrier, isolating its interior completely from the ocean. Chemical evidence showed that this was not entirely true. Water beneath the ice could remain isolated for long periods, but it was not permanently cut off. Connections existed, slow and hidden, allowing exchange over long timescales. These findings also revealed how sensitive the system is to change. Small shifts in circulation can alter chemical balances beneath the ice. Increased melting introduces more fresh water, changing salinity and density. These changes can modify circulation patterns, influencing where heat is delivered and how ice melts. Chemistry, circulation, vigor, and melting are tightly linked, forming feedback loops that amplify subtle changes over time. The chemical signatures beneath Antarctica also provided insight into history. Some water masses carried evidence of conditions that existed long before modern observation. They preserved records of past ice configurations, ocean circulation patterns, and interactions that shaped the continent over thousands of years. In this sense, the hidden ocean beneath Antarctica acts as an archive, storing information about Earth's past in dissolved form. Studying this archive, however, is slow and incomplete. Each expedition yields limited data. Many regions have never been sampled at all. Scientists must interpolate between known points, building models that remain uncertain. This uncertainty reinforces cautious interpretation and careful language. Discoveries are described not as final answers, but as pieces of a much larger puzzle. The shock for scientists lay not in any single chemical measurement, but in the emerging pattern. Beneath Antarctica exists a chemically complex ocean system, shaped by isolation, slow movement, and long-term interaction with ice and rock. This system behaves differently from any other marine environment on Earth, defying simple classification. Chemical signals also raised profound questions about life. Where chemistry is stable, where energy sources exist, and where water remains liquid, the possibility of biological activity arises. While life beneath Antarctic ice remains difficult to study directly, chemical conditions suggest that at least some regions could support microbial ecosystems adapted to extreme isolation and darkness. These discoveries deepen the sense that beneath Antarctica lies an environment both fragile and powerful. Fragile because disturbance could alter chemical balances that took millennia to develop. Powerful because these chemical processes influence ice stability and ocean circulation on a continental scale. Life, where no one expected it. For much of modern science, Antarctica was considered one of the most lifeless places on Earth. Its interior was assumed to be biologically silent, locked beneath ice, darkness, and pressure so extreme that survival seemed impossible. Even the surrounding ocean was viewed as sparse compared to warmer regions. Yet as scientists began to uncover the chemical and physical conditions beneath the Antarctic ice, an unsettling question emerged. If liquid water exists, if chemical energy is present, could life exist there as well? The idea was controversial. Life, as most people understand it, depends on sunlight. Plants use light to grow. Food webs begin at the surface. Beneath kilometers of ice, there is no sunlight at all. For decades, this absence was taken as proof that life could not exist beneath Antarctica. But discoveries in other extreme environments began to challenge this assumption. Deep sea vents, isolated caves, and buried sediments revealed that life does not always require light. It requires energy, water, and time. Chemical measurements beneath Antarctic ice suggested that energy sources were available. Reactions between water, rock, and dissolved minerals could provide chemical gradients capable of sustaining microbial life. These were not conditions for complex ecosystems, but they were enough for simple organisms adapted to extreme isolation. The realization that such conditions existed beneath Antarctica shifted scientific thinking once again. Evidence for life beneath the ice did not come from dramatic sightings, but from subtle signals. Chemical imbalances hinted at biological activity. Trace gases appeared in concentrations difficult to explain through physical processes alone. In rare cases where direct sampling was possible, scientists detected microbial signatures, organisms adapted to darkness, pressure, and scarcity. What made these findings especially shocking was the environment in which they were found. Beneath Antarctica, temperatures are near freezing. Pressure is immense. Nutrients are limited. Water movement is slow. These conditions demand extraordinary adaptation. Any organisms present must survive with minimal energy, growing slowly and persisting over long timescales. Life here does not thrive in abundance, it endures. These microbial systems, if present, are likely ancient. Isolated beneath ice for thousands or even millions of years, they may represent lineages that evolved separately from surface ecosystems. Their existence raises profound questions about resilience, adaptation, and the boundaries of life on Earth. It also forces scientists to reconsider what environments might be habitable elsewhere in the universe. Studying life beneath Antarctic ice is fraught with difficulty and responsibility. Any attempt to access these environments risks contamination. Introducing foreign microbes could permanently alter pristine systems that evolved in isolation. For this reason, the scientists approach biological investigation beneath Antarctica with extreme caution. Sterile drilling techniques, limited sampling, and strict protocols are essential, and even then, access is rare. This caution contributes to the perception that scientists avoid these regions. In reality, restraint is deliberate. The potential scientific value of studying life beneath Antarctica is enormous, but so is the risk of irreversible damage. Many researchers argue that understanding must proceed slowly, prioritizing protection over rapid discovery. The presence of life beneath Antarctic ice also complicates interpretation of chemical data. Biological processes can alter chemical signatures, making it difficult to separate physical from biological influences. This overlap adds another layer of uncertainty to an already complex system. Scientists must carefully consider multiple explanations for each signal they observe. These discoveries also reshape how Antarctica is viewed as a system. Beneath the ice, geology, chemistry, and biology intersect. Water interacts with rock, producing energy. That energy may sustain life. Life, in turn, may influence chemistry and circulation. This interconnectedness challenges simple models and demands interdisciplinary approaches. The shock of discovering potential life beneath Antarctica lies not in its abundance, but in its persistence. In an environment defined by extremes, life may have found a way to exist quietly, slowly, and invisibly. This possibility transforms Antarctica from a frozen void into a place of subtle activity, where even the harshest conditions do not completely silence biology. Why scientists move slowly beneath Antarctica. The discoveries beneath Antarctica did not trigger a rush to explore every hidden cavity or subglacial sea. Instead, they led to something far quieter: restraint. As evidence mounted that liquid water, complex chemistry, and even potential life existed beneath the ice, scientists became increasingly cautious. Beneath Antarctica, the challenge is not only how to discover, but how to do so without causing harm that cannot be undone. One of the greatest concerns is contamination. The environments beneath Antarctic ice have been isolated for immense spans of time. Water trapped under kilometers of ice may have remained sealed from the surface for hundreds of thousands of years. Introducing even a small number of surface microbes could permanently alter these systems. Unlike surface environments, recovery here would not occur on human timescales. Any disturbance could persist indefinitely. This risk fundamentally changes how research is conducted. Drilling through ice is not a simple act. Equipment must be sterilized to extreme standards. Fluids used during drilling must be carefully controlled. Every step is designed to minimize contact between surface materials and subglacial environments. These precautions slow progress and limit how often access is attempted, but they reflect an understanding that discovery without protection can lead to irreversible loss. There is also the issue of physical disturbance. Beneath Antarctica, systems operate slowly and delicately. Currents move at measured paces. Chemical balances develop over long periods. Even the placement of an instrument can alter water flow or sediment structure. And in such environments, observation itself becomes an intervention. Scientists must constantly weigh the value of data against the risk of altering the very system they wish to understand. Ethical responsibility plays a growing role in polar research. Antarctica is governed by international agreements that emphasize preservation and scientific cooperation. These agreements reflect a shared recognition that the continent and its hidden environments belong to no single nation. Decisions about exploration beneath the ice are therefore collective, shaped by caution and consensus rather than competition. Another reason scientists move slowly is uncertainty. Despite remarkable discoveries, knowledge of what lies beneath Antarctica remains fragmentary. Many conclusions are based on limited data collected from a small number of sites. Expanding exploration too quickly could lead to misinterpretation or overconfidence. By proceeding carefully, scientists allow understanding to evolve gradually, guided by evidence rather than assumption. Technology also imposes limits. Tools capable of operating beneath kilometers of ice are complex and fragile. Failures are common, and recovery is often impossible. Each mission represents years of preparation and significant investment. Moving slowly reduces risk, preserves resources, and allows lessons learned from one expedition to inform the next. There is also a recognition that some environments may be better left undisturbed for now. As techniques improve, future researchers may be able to study these systems more safely and effectively. By limiting access today, scientists preserve the possibility of deeper understanding tomorrow. This long-term perspective contrasts sharply with the idea of rapid exploration and highlights a different philosophy of discovery. The shock beneath Antarctica did not come with urgency or panic. It came with reflection. Scientists realized that they were not just uncovering new data, but encountering systems that challenge assumptions about isolation, stability, and life itself. Such systems demand patience. Moving slowly beneath Antarctica is not a sign of hesitation or fear. It is a recognition of scale. The processes at work unfold over centuries and millennia. Human observation occupies only brief moments within that timeline. Respecting that difference shapes how science proceeds. Technology pushed to its absolute limits. Exploring beneath Antarctica is not a matter of curiosity alone. It is a test of technology at its most extreme. The environments hidden under kilometers of ice are among the harshest on Earth, and humans cannot enter them directly. Every discovery made beneath Antarctica depends on machines designed to survive pressure, darkness, isolation, and cold far beyond ordinary limits. As scientists pushed deeper beneath the ice, they discovered that technology itself became one of the greatest challenges. Drilling through Antarctic ice is the first barrier. Ice is not uniform. It contains layers, fractures, and internal stresses formed over thousands of years. Drills must operate with precision, maintaining sterility while melting or cutting through hundreds of meters of ice. Any failure can trap equipment permanently, sealing off access and ending a mission. Even successful drilling creates only a narrow passage, barely wide enough for instruments to pass through. Once beneath the ice, technology faces an environment without orientation. There is no GPS signal, no visual landmarks. Autonomous underwater vehicles must rely on internal navigation systems and acoustic signals that travel slowly through water. Errors accumulate silently. A vehicle may drift slightly off course, then further until recovery becomes impossible. Many missions end not with dramatic failure, but with the quiet loss of contact. Communication beneath Antarctica is limited and fragile. Signals must pass through water and ice, often relying on sound rather than radio waves. Data transmission is slow and restricted. Scientists may wait hours or days to receive confirmation that an instrument is still functioning. When something goes wrong, there is often no way to intervene. The machine must endure alone or fail alone. Power is another constraint. Batteries degrade faster in cold environments. Replacing them requires retrieval, which may not be possible for years. Instruments must be designed to conserve energy, collecting data slowly and selectively. This limits resolution and frequency of measurements, forcing scientists to prioritize what they observe. Every data point is a compromise between curiosity and endurance. Sensors themselves face degradation. Extreme pressure can alter calibration. Chemical exposure beneath ice shelves can corrode components. Fine sediments can clog delicate instruments. Even when a device survives physically, its measurements may drift over time. Scientists must account for this uncertainty when interpreting results, aware that even the most advanced tools have limits beneath Antarctica. Despite these challenges, technological innovation has driven discovery. Ice-penetrating radar revealed subglacial seas. Sonar mapping uncovered channels beneath ice shelves. Autonomous vehicles provided the first direct observations of hidden cavities. Each advancement expanded what was possible, while also revealing new complexities and new limitations. Technology also shapes the pace of discovery. Missions are planned years in advance. Each expedition builds on lessons from the last. Failures are studied as carefully as successes. This slow, iterative process contrasts sharply with the dramatic imagery often associated with exploration. Beneath Antarctica, the progress is measured not in rapid breakthroughs, but in gradual expansion of what can be observed safely. The shock for scientists was not that technology struggled beneath Antarctica, but that it succeeded at all. That any data could be collected in such an environment was remarkable. Yet each success highlighted how much remained beyond reach. Vast regions beneath the ice have never been visited, never measured, never mapped. Technology illuminates only small pockets of a much larger system. As tools improve, scientists face new decisions. More capable machines could reach deeper, stay longer, and collect more data. But increased capability also increases responsibility. The risk of disturbance grows with access. Each technological step forward must be weighed against ethical and environmental considerations. Technology beneath Antarctica is not just a means to an end. It is part of the story itself. The discoveries made there reflect not only what exists beneath the ice, but what humans are capable of observing in environments that resist presence. Storms above, consequences below. At first glance, the storms that circle Antarctica seem far removed from the hidden ocean beneath the ice. How could wind and waves at the surface influence water sealed under kilometers of frozen mass? For many years, scientists assumed that the ice acted as a barrier, isolating what lay beneath from the chaos above. But as observations accumulated, this assumption began to fade. Even beneath Antarctica, the atmosphere leaves its mark. The Southern Ocean is one of the stormiest places on Earth. Powerful winds circle the continent almost continuously, with driving waves and shifting surface waters. These storms do more than shape the surface. They influence ocean circulation on a scale that reaches far below, setting in motion changes that eventually propagate beneath ice shelves. The connection is indirect, but persistent. When storms intensify winds, they alter how surface waters move and mix. This mixing affects the formation and movement of deeper water masses. Changes at the surface can strengthen or weaken currents that travel along the continental shelf. Over time, these shifts influence how much relatively warm water reaches the underside of ice shelves. A storm may pass in days, but its influence can linger for months beneath the ice. Scientists began to notice correlations between atmospheric patterns and changes beneath Antarctica. As periods of stronger winds were followed by increased delivery of heat to ice shelf cavities. These patterns were subtle and difficult to confirm, but they appeared consistently across different regions. The realization that storms above could influence melting below added another layer of complexity to an already intricate system. Pressure changes also play a role. Large storm systems alter atmospheric pressure over the ocean, causing the sea surface to rise or fall slightly. These changes may seem insignificant, but beneath ice shelves, even small pressure variations can influence water movement. Over time, these fluctuations contribute to the circulation patterns that carry heat beneath the ice. The unpredictability of storms makes their influence especially challenging to study. Weather patterns shift rapidly, and long-term trends are difficult to isolate from natural variability. Beneath Antarctica, where data is sparse, linking cause and effect requires careful analysis and cautious interpretation. Scientists must rely on limited observations and models that attempt to bridge the gap between atmosphere and ocean. This connection between storms and sub-ice processes challenges the idea of Antarctica as an isolated system. The ice does not simply respond to local conditions. It responds to forces generated far away, transmitted through the ocean in slow, indirect ways. This realization broadened scientific understanding of how deeply interconnected Earth's systems truly are. The shock lies not in dramatic impact, but in reach. Storms that never touch the ice directly can still influence what happens beneath it. The atmosphere and ocean work together, shaping Antarctica from above and below. This coupling means that changes in weather patterns can have consequences that extend far beyond the surface. For scientists, this discovery reinforced the need for integrated study. Understanding beneath Antarctica requires looking not only at ice and water, but at the atmosphere as well. Each layer influences the others, forming a system that resists simple explanation. Narrow time windows beneath Antarctica. Beneath Antarctica, discovery is governed not only by science and technology, but by time. Access to the hidden ocean below the ice is limited to brief, fragile windows that open and close without warning. These windows shape every expedition, every measurement, and every decision scientists make. Missing one opportunity can mean waiting years for the next. And this reality plays a quiet but decisive role in why so much beneath Antarctica remains only partially understood. Antarctic research is constrained by seasons. For much of the year, darkness, extreme cold, and ice conditions make operations impossible. Only during the short austral summer do conditions allow ships to approach the continent, aircraft to land safely, and drilling operations to proceed. Even then, weather can change rapidly, turning calm seas into dangerous conditions within hours. Scientists often arrive with detailed plans, only to find those plans reshaped by forces beyond their control. These narrow windows place immense pressure on each mission. Equipment must function flawlessly. Timing must align precisely. Delays caused by storms, mechanical issues, or unexpected ice movement can cancel entire operations. In regions beneath Antarctica, there is rarely a second chance. If an instrument fails or a drill hole closes, returning to the same site may not be possible for years. Time constraints also limit how long instruments can remain beneath the ice. Long-term monitoring is essential for understanding slow processes such as melting, circulation, and chemical change. Yet deploying and maintaining instruments over extended periods is extraordinarily difficult. Batteries degrade, sensors drift. Recovery depends on returning during another narrow window. As a result, data often comes in fragments, snapshots rather than continuous records. Scientists must then reconstruct long-term behavior from these fragments. Patterns are inferred cautiously. Uncertainty remains high. This incomplete picture is not due to lack of effort, but to the reality of working beneath Antarctica. Time does not accommodate persistence easily here. The psychological weight of time also shapes research decisions. Crews and scientists know that every hour matters. Fatigue accumulates. Decisions must be made quickly, sometimes under pressure. Safety remains paramount, and caution often outweighs ambition. When conditions are marginal, operations are postponed or abandoned. Beneath Antarctica, restraint is often the wiser choice. Funding cycles further compound these limits. Research programs are planned years in advance, with expectations for results within defined timeframes. Delays caused by missed windows can jeopardize future support. Regions that consistently resist access may be deprioritized, not because they lack importance, but because time itself works against sustained study. The shock beneath Antarctica is not just what scientists discover, but how rarely they are able to discover it. Each successful mission represents the alignment of countless factors: weather, technology, logistics, and timing. When that alignment fails, the ice remains closed, and the hidden ocean continues its quiet work unseen. The cost of reaching beneath Antarctica. Every discovery beneath Antarctica carries a hidden price, not just in effort or time, but in resources measured carefully and spent cautiously. Studying what lies beneath the ice is among the most expensive scientific endeavors on Earth. Ships, aircraft, drilling systems, autonomous vehicles, fuel, personnel, and years of preparation all converge for missions that may last only weeks. In this environment, a cost is not an abstract concern. It is a constant presence, shaping what scientists attempt and what they choose not to pursue. Reaching Antarctica itself is costly. Research vessels must travel vast distances through some of the roughest seas on the planet. Fuel consumption is immense. Ice-strengthened ships require specialized maintenance. Crews are highly trained, and their safety demands redundancy in systems and equipment. Once near the continent, operations slow further. Ice conditions dictate routes. Weather limits movement. Every delay adds expense. Accessing what lies beneath the ice multiplies these costs. Drilling through hundreds or thousands of meters of ice requires equipment designed for extreme cold and precision. Each drill system must be transported, assembled, tested, and operated under conditions where failure is common and repair is difficult. A single malfunction can end a mission, leaving expensive equipment trapped beneath the ice. Autonomous underwater vehicles used beneath ice shelves represent another major investment. These machines are custom-built, equipped with sensors, navigation systems, and power supplies designed for isolation. Losing one beneath the ice is not just a technical setback. It is a significant financial loss. Recovery is often impossible. As a result, every deployment involves careful risk assessment, balancing potential discovery against the likelihood of loss. Long-term monitoring beneath Antarctica is particularly expensive. Instruments designed to operate for months or years must be built to endure pressure, cold, and chemical exposure. Batteries must last without replacement. Data storage must be secure. Retrieval requires returning to the same site during another narrow access window. When retrieval fails, years of data and the investment behind it are lost. Funding for such work is limited and competitive. Research programs must justify their goals clearly and demonstrate likely outcomes. Regions beneath Antarctica that resist repeated access or produce fragmented data are difficult to sustain financially, no matter how scientifically valuable they may be. Over time, this reality shapes research priorities, concentrating effort where returns are more predictable. Cost also influences collaboration. Many Antarctic projects rely on international partnerships to share expense and expertise. Coordinating such efforts adds complexity. Schedules must align. Resources must be pooled. When conditions disrupt plans, the ripple effects extend across institutions and nations. These challenges further encourage cautious, deliberate exploration rather than rapid expansion. The shock beneath Antarctica, then, is not just scientific. It is logistical and economic. Discoveries emerge slowly because they are expensive to obtain. Each insight represents years of investment, planning, and restraint. This reality explains why vast areas beneath the ice remain unexplored, not due to lack of interest, but due to the immense cost of reaching them responsibly. What scientists still cannot measure beneath Antarctica. Despite decades of effort, technological innovation, and careful exploration, much of what lies beneath Antarctica remains beyond direct measurement. But this absence of data is not a failure of science, but a reflection of the environment itself. Beneath kilometers of ice, where darkness is permanent and pressure is immense, even the most advanced tools struggle to provide continuous, reliable observation. What scientists know is substantial. What they cannot yet measure may be even more significant. One of the greatest challenges is scale. Antarctica is vast, and the environments beneath it are equally expansive. Ice shelves alone cover areas larger than many countries, with hidden cavities stretching far inland. Subglacial seas are scattered across the continent, connected by channels that remain largely unmapped. The sheer size of these systems means that any single expedition can observe only a tiny fraction of the whole. Scientists must extrapolate from limited data, are aware that unseen regions may behave differently. Continuity is another major limitation. Most measurements beneath Antarctica are temporary. Instruments are deployed for months or a few years at most, then recovered or lost. Continuous, multi-decade records are extremely rare. Without long-term data, it is difficult to distinguish short-term variability from lasting change. A period of increased melting may represent a temporary fluctuation rather than a trend. But without extended observation, certainty remains elusive. Many regions beneath Antarctica have never been directly sampled. Thick ice, unstable terrain, and inaccessible cavities prevent entry. In these places, scientists rely on indirect evidence. Radar reflections, gravity anomalies, subtle changes in ice motion. These methods are powerful, but they provide incomplete pictures. They reveal the presence of water, channels, or cavities, but not their detailed behavior or evolution over time. Chemical processes beneath the ice also remain poorly constrained. While sampling has revealed complex chemistry in some locations, vast areas remain unsampled. Chemical reactions unfold slowly, influenced by pressure, temperature, and interaction with sediment. Without repeated measurements, understanding these processes remains speculative. Scientists can identify possibilities, but confirmation requires access that is not yet feasible. Biological uncertainty is perhaps the most profound unknown. Evidence suggests that microbial life may exist beneath Antarctic ice, but its distribution, diversity, and activity are largely unknown. Direct biological sampling is rare and conducted under strict limitations to prevent contamination. As a result, scientists know that life may exist, but not how widespread it is or how it interacts with its environment. These questions remain open, awaiting future advances. Water movement beneath Antarctica also resists full measurement. Currents trapped beneath ice shelves move slowly and unpredictably. Mapping their pathways requires long-term tracking that current technology struggles to provide. Models attempt to fill these gaps, but models depend on assumptions that may not hold everywhere. Without comprehensive data, uncertainty persists. The interaction between the ocean, ice, and seafloor beneath Antarctica is another area of limited measurement. Changes in one layer influence the others, creating feedbacks that are difficult to isolate. For example, thinning ice alters pressure, which affects water circulation, which influences melting patterns. Measuring these interactions simultaneously across large areas remains beyond current capability. Even when data is collected, interpretation is challenging. Instruments may drift out of calibration. Signals may reflect local anomalies rather than broader patterns. Scientists must account for uncertainty at every step, building conclusions cautiously and revising them as new information emerges. This slow, iterative process contrasts with the dramatic expectations often associated with discovery. The shock beneath Antarctica, then, is not just what has been found, but how much remains unknown. The hidden ocean beneath the ice is not a single system, but a network of interacting environments operating over timescales far longer than human observation. Scientists have glimpsed parts of this network, enough to recognize its importance, but not enough to describe it fully. This uncertainty shapes scientific behavior. Researchers do not rush to conclusions. They acknowledge gaps openly. They design experiments that minimize risk and maximize learning, even if progress is slow. Beneath Antarctica, patience is not optional. It is essential. The inability to measure everything also serves as a reminder of humility. Earth still contains environments that resist complete understanding. Antarctica, often perceived as static and silent, reveals itself as dynamic and complex when examined closely. Yet it also reminds scientists that knowledge has limits. While much of beneath Antarctica remains untouched, with so much revealed beneath Antarctica, a natural question arises. If scientists know that liquid water, active currents, complex chemistry, and even potential life exist beneath the ice, why does so much of this hidden world remain untouched? The answer is not indifference, nor lack of curiosity. It is a deliberate choice shaped by experience, responsibility, and respect for an environment that does not easily forgive intrusion. Beneath Antarctica, every action carries lasting consequences. Unlike surface environments, where disturbance can be diluted or repaired over time, the systems beneath the ice recover slowly, if at all. Water trapped beneath kilometers of ice may remain isolated for tens of thousands of years. Sediments settle undisturbed. Chemical balances evolve gradually. Introducing change into such a system is not a temporary event. It becomes part of its long-term history. Scientists understand that exploration is not neutral. Drilling through ice alters pressure. Deploying instruments changes water flow. Even the presence of artificial light and heat can disrupt fragile conditions. In environments that have evolved without surface influence, these changes matter. This understanding has led to a shift in philosophy. Beneath Antarctica, restraint is considered a form of stewardship rather than limitation. International agreements governing Antarctic research reinforce this approach. Antarctica is protected by treaties that prioritize peaceful use and scientific cooperation. Beneath its ice lies an extension of that responsibility. No single nation controls these hidden environments. Decisions about exploration are made collectively, with emphasis on preservation and shared knowledge. This framework encourages careful deliberation rather than rapid expansion. There is also the reality that not all environments must be explored immediately. Scientists recognize that future technologies may allow safer, less invasive access. By leaving some regions untouched today, they preserve the possibility of better understanding tomorrow. This long-term view contrasts sharply with earlier eras of exploration, where discovery often came at the cost of irreversible change. Avoidance beneath Antarctica is therefore selective, not absolute. Scientists choose where to focus their efforts, targeting regions where data can be collected responsibly and where risks are manageable. Other areas are left unvisited, not because they lack importance, but because current methods are insufficient to study them without unacceptable impact. The shock beneath Antarctica lies partly in this restraint. In a world driven by rapid discovery, Antarctica demands patience. It reveals that some of the most important systems on Earth operate beyond the pace of human ambition. Respecting those systems means accepting limits. Beneath the ice, the ocean continues to move, melt, mix, and evolve, regardless of whether it is observed. Scientists have learned that understanding does not require total access. It requires careful listening to the signals that can be detected without intrusion. As the documentary approaches its conclusion, attention will shift to what this hidden world beneath Antarctica means for the future. Not predictions or alarm, but understanding. How these discoveries reshape how scientists think about Earth as a connected system, and why the quiet processes beneath the ice matter far beyond the frozen continent itself. The ocean beneath Antarctica is still changing. One of the most unsettling realizations to emerge from decades of research beneath Antarctica is this: nothing there is finished. The hidden ocean beneath the ice is not a frozen relic of the past, preserved unchanged beneath kilometers of ice. It is a system in motion, slow, quiet, and largely invisible, but continuously evolving. Scientists once believed that whatever lay beneath Antarctica would change only over geological timescales. What they now understand is that change is already underway, unfolding beneath the ice in real time. The movement is subtle. There are no sudden waves, no dramatic ruptures that announce transformation. Instead, change beneath Antarctica appears as gradual shifts in temperature, small alterations in circulation, and slow thinning of ice from below. These processes operate beneath the threshold of human perception. They are detected only through careful measurement, comparison, and patience. Yet when viewed over decades, their significance becomes clear. Ocean water beneath Antarctica responds to forces far beyond the continent itself. Changes in distant ocean basins influence the Southern Ocean. Shifts in wind patterns alter circulation. Variations in sea ice formation affect how heat is distributed. These changes propagate slowly, carried by currents that eventually reach the ice shelves and subglacial cavities beneath Antarctica. By the time their influence is felt under the ice, when the original cause may be thousands of kilometers away. One of the clearest signs of ongoing change beneath Antarctica is the evolving pattern of heat delivery to ice shelves. Measurements taken years apart reveal differences in temperature and circulation that cannot be attributed to chance alone. In some regions, relatively warm water is reaching further beneath the ice than before. In others, circulation pathways appear to be shifting. These changes are small in magnitude, but they accumulate over time, reshaping how ice interacts with the ocean below. The ice itself responds slowly, but persistently, As the base of an ice shelf thins, its structure weakens. This alters how stress is distributed across the ice, changing the way it flexes and flows. These mechanical changes feed back into ocean circulation, modifying the shape of cavities beneath the ice and influencing where water can travel. Beneath Antarctica, change rarely occurs in isolation. Each shift triggers another, forming a chain of quiet adjustments. Subglacial water systems are also evolving. Channels beneath the ice may widen or narrow as pressure and flow change. Water stored beneath the continent may be released or redistributed, affecting ice motion above. These processes are difficult to observe directly, but indirect evidence suggests that the subglacial network is far more dynamic than once assumed. Beneath the ice, water is not simply present, it is active. Chemical signatures reinforce this picture of change. Repeated sampling shows variations in salinity, gas concentrations, and dissolved elements over time. These changes indicate ongoing mixing between isolated waters and the broader ocean system. They suggest that beneath Antarctica, isolation is not absolute. Connections open and close, allowing exchange that reshapes chemical balances slowly but steadily. Biological systems, if present, are likely responding as well. Microbial life beneath Antarctica would be exquisitely sensitive to changes in chemistry and energy availability. Even small shifts in circulation or chemical input could alter biological activity. Yet these changes would unfold invisibly, detectable only through subtle chemical clues. Understanding these responses remains one of the most challenging aspects of Antarctic science. What makes these ongoing changes particularly difficult to grasp is their pace. Human attention is drawn to rapid events. Storms, collapses, sudden shifts. Beneath Antarctica, change operates on a different rhythm. Years, decades, and centuries matter more than days. Scientists must therefore think in longer terms, assembling patterns from incomplete data collected over extended periods. This slow pace also complicates communication. Explaining quiet change beneath Antarctica is difficult in a world accustomed to dramatic narratives. Yet for scientists, the absence of spectacle does not diminish importance. If anything, it increases concern. Processes that operate quietly are harder to monitor and easier to overlook, even as they reshape fundamental systems. The realization that the ocean beneath Antarctica is still changing has reshaped research priorities. Scientists now emphasize long-term monitoring, even when data collection is difficult and incomplete. They seek to understand trends rather than events, patterns rather than anomalies. This approach reflects an understanding that beneath Antarctica, significance lies not in moments, but in persistence. Despite growing awareness, uncertainty remains high. Many regions beneath the ice have never been measured, let alone measured repeatedly. Scientists must acknowledge that their picture of change is partial. There may be processes underway that remain entirely unseen, shaping the system in ways not yet imagined. This uncertainty reinforces caution and humility in interpretation. The shock beneath Antarctica is not that change is occurring, but that it was once assumed not to. The idea of Antarctica as a frozen, unchanging world has proven incomplete. Beneath the ice, the ocean moves, responds, and evolves, quietly linking the continent to the rest of the planet. Beneath Antarctica, the quietest shock in the end. The most shocking discovery beneath Antarctica is not a single feature, not a channel, a sea, or a trace of life. It is the realization that one of the most remote places on Earth is not static, not sealed, and not separate. Beneath the ice, Antarctica is part of a living planetary system connected quietly and persistently to oceans, atmosphere, and time itself. This understanding reshapes how scientists see the continent and how they see Earth as a whole. For generations, Antarctica symbolized permanence, a frozen anchor at the bottom of the world, ice that appeared ancient, immovable, and indifferent to change. That image was reinforced by distance and difficulty. Few could reach it. Fewer still could look beneath it. And what scientists have now revealed does not erase that image, but it softens it, revealing motion where stillness was assumed and interaction where isolation was expected. The ocean beneath Antarctica does not announce itself. It does not roar or surge. It flows patiently, guided by pressure, temperature, and shape. It carries heat so subtly that its effects take years to register. It melts ice not violently, but persistently. This quiet nature is precisely why it remained hidden for so long. Human perception is tuned to sudden change. Beneath Antarctica, change whispers. This whisper matters because it reveals how Earth truly functions. No part of the planet operates alone. The ice above responds to water below. The water below responds to forces far away. Winds over distant oceans influence currents that slip beneath ice shelves. Yet heat stored thousands of kilometers away arrives beneath Antarctica years later, delivered without spectacle. This interconnectedness challenges simple cause and effect thinking and demands patience from science. The discoveries beneath Antarctica also redefine what exploration means. In earlier eras, exploration meant reaching new places, planting flags, claiming knowledge. Beneath the ice, exploration is quieter and more restrained. It means listening to indirect signals. It means accepting incomplete answers. It means knowing when not to proceed. Scientists have learned that access is not always progress, and restraint can preserve understanding rather than limit it. This restraint reflects a deeper shift in scientific mindset. Beneath Antarctica, the goal is no longer total mapping or complete control. It is comprehension without domination, protection alongside curiosity. The recognition that some systems are so slow, so isolated, and so fragile that human intervention must be measured carefully or not at all. The shock, then, is philosophical as much as physical. Antarctica reveals that even now, in an age of satellites and sensors, Earth still contains environments that resist full understanding, not because they are mysterious in a dramatic sense, but because they operate on scales of time and subtlety that exceed human rhythms. Beneath the ice, water remembers. Chemical signatures record ancient isolation. Sediments preserve histories of flow and change. Ice itself carries layers of past climates. The hidden ocean beneath Antarctica is an archive, storing information about Earth's evolution in ways that are only beginning to be read. Each discovery adds a line to that story, while leaving many pages unread. These revelations also carry meaning beyond Antarctica. They inform how scientists think about stability elsewhere, on other ice sheets, in other oceans, even on other worlds. The idea that liquid water can persist beneath ice, isolated yet active, reshapes assumptions about habitability and planetary behavior. Antarctica becomes not just a subject of study, but a reference point. Yet for all that has been uncovered, humility remains central. Scientists acknowledge how much remains unknown. Vast regions beneath the ice have never been observed directly. Many processes are inferred rather than measured. Models remain provisional. This openness about uncertainty is not weakness. It is an honest response to an environment that does not yield easily to observation. The ocean beneath Antarctica teaches patience. It teaches that importance is not always loud, that influence does not require visibility, that systems shaping the future of ice and ocean can operate silently for centuries before their effects become clear. It reminds us that absence of drama does not mean absence of significance. As this documentary comes to a close, the image of Antarctica changes subtly. It remains cold, distant, and formidable. But it is no longer inert. Beneath its ice, water moves. Chemistry evolves. Life may persist. Change unfolds slowly, quietly, and relentlessly. The most shocking discovery beneath Antarctica is not what scientists have found, but what they have learned to expect. Motion beneath stillness, a connection beneath isolation, change beneath permanence. And as long as the ice remains, the ocean beneath it will continue its quiet work, unseen, unheard, shaping a continent from below. As we reach the end of this journey, the image of Antarctica slowly changes. What once seemed like a silent, frozen continent reveals itself as something far more complex. Beneath the ice, the ocean moves, not quickly, not violently, but with patience and persistence that spans centuries. There are no sudden sounds beneath Antarctica, no crashing waves, no visible storms. Yet change is always underway. Water flows through hidden channels. Heat travels quietly beneath ice shelves. Chemistry evolves in darkness. And in places where life was once thought impossible, existence may continue, slowly and silently. The discoveries scientists have made beneath Antarctica are not dramatic in the way stories often expect. They are subtle. They unfold gradually. And that is what makes them profound. They remind us that the most important forces shaping our planet do not always announce themselves. Antarctica does not resist study because it is empty. It resists because it is delicate, ancient, and deeply interconnected with the rest of the Earth. Beneath the ice, the ocean does not wait to be observed. It continues its quiet work, whether it is seen or not. Ice forms, ice melts, water moves, slowly, constantly, patiently. And long after research ships have departed, instruments have gone silent, and the surface returns to stillness. Mas, the hidden ocean beneath Antarctica remains in motion, shaping the future in ways that may take generations to fully understand. This is not a place of noise or urgency. It is a place of time. Thank you for watching. Let the ocean rest, and let the silence continue.